Okay, so just now we introduced some common properties of the representative elements. So now introduce the D block metals. So basically, this part of elements are called D block D block metals. So basically, they have 4 series. So each one have 10 elements. And we can see there are each additional electron enters the 3D substrate. But for this CR and CU, they have the 4s1 3D1 and 4s1 3D10 electrical configuration. And we will also introduce why they have this kind of electrical configurations. Okay, so here we can see the electrons are filled in the D block elements. So, for example, when the electrons are filled in 3p orbitals, the next one will be filled in the 4s. Okay. And then when 4s has 2 electrons, the last one will put in 3D. Okay, for example, first this one put in here 3D1. So this element is D block element. Okay. So for example, for this one, the first D block element, it has like 3s2, 3p6, 4s2, 3d1. Okay. And the second one, of course, will be 3d2, right? Okay. So for example, here to show the electric configuration of like the 3D orbitals with 3D orbital electrons. So the first one is put here, and the second one is put here, and the third one, fourth one. So for CR, we can see it has. So basically, for others, they have 2 4s electrons. Okay, but for this one, it has only one. One is in here. Put one is here, because in this configuration, this is called half field orbital. Okay, so in this case, the half field orbital is also stable. Then this one. Okay, so this, for example, this is if this one put here, so this is full, this is not full. Okay, so basically in this way is more stable. So here we can see the half filled and the completely filled with electrons are stable. Yeah.
I'm sorry, could you repeat what you said?
Okay. So for example, in this one, the electron put here, right? So for this one, so the electron should be put here, and here should have 2, right? But in this case, this one will one of this electron will move from 4s to 3D. So using this way, we can see here is half filled, right? Here is a half filled. So the whole are half filled. Yeah. So half filled is stable. Then for example, then this case, if here is full, here is not half. Okay, but both of half are stable. Then one is full, one is uncompleted, uncompleted. Okay. Yeah. So and also for this one, also for carbon and for a copper. So here, one electron also will move from 4s to here. From this way, we can say this is half, this is full, this is half. And this full, if this one put here, so this is full, but this is uncomplicated, right? But using this way, one is completed, another one is half. So this is stable, this stable. So here, these two elements are different from others. The reason is because the half field and the completed field with electrons are stable. So they're using this way to field the electrons. Okay. So basically, what is transition metal? So here we can see the transition metals means they have d block electrons, d orbital electrons, and basically they have single electrons. For example, here we can see this has single electrons, right? But this one has or not single electrons. Zinc? No. Yes. So we know if the element has single electrons, this means it will show magnetic properties, right? So for this one, but for zinc, it doesn't have magnetic properties. But for others, if they have single electrons, they will show magnetic properties. So this is about the d block metals. All the elements are metals, and most of them are magnetic. The reason is they have a single electron. And here also shows some very common properties of the d block metals, or like transition. We also call them transition metals. So basically, they have like high melting point and the boiling point. The reason is for the metals, they have mechanical bond, okay, between the atoms, so they are very stable, and so they have high melting point and boiling point. And also they have some good mechanical properties. And but we know mercury has lost melting point, but this is totally different from other metals. Okay, so here we also can see the metals. Basically, the metals will lose electrons. So they can show positive charges. And usually, first they lose the electrons in the outermost s orbital. Okay. Basically, they have like 4s2 electrons, right? So these two s orbital electrons are very easy to lose. And they will also show different chemical properties. So this slide shows the oxidation states of the transition metals. From here we can see, so for this one, from left to right, so this one and this one, basically they have only have one kind of charge. So this one to show plus one charge, and this one can only show plus 2 charge. But for this, they can show more kinds of charges. For example, for this one, they have more d electrons, so they can show different charges. Okay, so here is about the oxidation states of transition metals. So basically, the low oxidation states found in simple ionic compounds. For example, for this simple compounds, they show low oxidation states. But for some transition metals in higher oxidation states, usually covalently bound to electronegative elements like oxygen and fluorine. We know the oxygen and fluorine, they have high electronegativity, so they can accept more electrons from the metals. So the metals can show high oxidation states. For example, in this case, it like show +7 charge. This is loose. All d block electrons when it compound with oxygen. Okay, and the change of the oxidation states. So, if the compounds containing the transition metals in high oxidation states, they tend to be oxidation agents. This means, for example, in this case, the metal has high oxidation state, like in +7 charge, right? +7 charge. So +7 charge means it's very easy to get the electrons. So they are oxidation agents. And for these metals, they have low oxidation states. So basically, they can continue to lose electrons. So they are often called like reducing agents. And of course, here just simply introduce. They are like some common properties. Okay, and basically, for example, for chemistry students, for each element, for each group, there will be using one chapter, each chapter to just introduce the properties of one group. Okay, but here we're just using very few time to simply introduce their properties. Okay, and here also some example. For some metals, they can be strong reducing agents, but for some cations, they may be as a strong oxidation agent. Okay, and also one important properties about the d block metals is they are catalytic activity. Catalytic. So we know many in industry, many metals are used as catalytic system. So why they can be the catalyst? Because they have some empty d orbitals. So this empty d orbitals can accept electrons from other compound or other atoms, so they can show the kinetic properties.
So what is it catalytic?
Okay. Here example. Here very good example to show there are catalytic properties. For example, for this reaction, the ethylene changes to ethylene. So basically, like this organic compound, okay, get a hydrogen, react with hydrogen to form this. So you know this, right? This is a double bond. Double bond, okay. So we will need to know this in later, okay, other chapters. So this is double bond. So this double bond one bond can be broke, and then it can accept. For each carbon can accept one hydrogen, right? To get this from this. So basically, this reaction is very difficult to happen. It's very difficult, but we can use nickel as catalyst to, so this reaction will become very fast. Why? Because at first, for example, these two molecules like this in here, right? This is nickel surface. We know nickel has empty d orbitals, right? This empty d orbitals can accept electrons from hydrogen and the carbon. So the hydrogen will like coordinated with the nickel and form very weak this bond. This means one electron from hydrogen move to the empty d orbital of nickel to form very weak bond, right? They share one electron. This electron come from hydrogen. Okay. And also it can accept one electron from this carbon, form very weak. So when they form this bond, so now the first step forms this weak bond. Second step, so they can break those hydrogen and then continue to break to show two electrons with hydrogen. Now this is very active. So this can easily move to here, move to carbon, and then hydrogen connect with carbon. So firstly, the nickel accept the electrons from the hydrogen and the carbon. So using this way, the hydrogen bond easy to be broke, and the carbon also one bond also broke. When they broke, and they become active atom, hydrogen atom, and then they are easy to form carbon hydrogen bond, So this is the process of the this is a catalytic process of this reaction. Okay, so this is just one sample to show the catalyst how to work, how the catalyst work. Okay. So basically, the transition metals, they are like they have many 3D and 4S electrons, and also they can change the oxidation states. This means they can basically lose electrons, and they lose different numbers of electrons, so they can show different kinds of positive charges, and also they can be good catalysts. Okay, now introduce the inner transition element. So here we say this is called D block elements, or like D block metals. All the valence electrons are filled in like D orbitals, right? D orbitals. But we know after when the 5D orbitals are filled, the next orbital will be is 4F. So some electrons will be filled in 4F orbitals. When the 5D orbitals are fully filled, okay, and then the electrons will be filled into the F orbitals. So this kind of elements are called, you can say also like F block elements. F block, but there are only two kinds of F block elements. One is 4F, another is 5F. So 4F, basically we call them lens lines. So the first field is called like lens lines. The second series of elements is called actin lines. So for actin lines, their electrons are filled in 5F orbitals. So this is also called inner transition metals. Okay, so the lens lines basically there are electric configurations like this: 6s2 and 4f from 0 to 14, and then D 5D maybe 1 or 2. Oh no, here is before field 4f. There are 3D. There are 4D are filled. 4D are filled. When 4D orbitals are filled, and then the electrons will be filled in 5F. Okay, not 5D, 4D. When the 4D orbitals are filled, and then the electrons will be filled in 5D. Okay, and when the 5D orbitals are filled, then the electrons will be filled in 5F. Okay, so 5F is this. So the electron lens lines is 4F0 to 14. So total how many elements? There are 15 elements. Okay, there are 15 elements in this series. And these elements are so similar, very similar, because the difference between the 4F is very small. So there are chemicals chemical or physical properties are also very similar. At the first step, people also call them like real Earth elements, because at first people think they are very real in the Earth, so they call them. But in fact, they are not. They are not so real. For example, this is the abundance of elements in Earth. Yes, we can say for landslides here, okay, they have more than these elements, right? For example, if you like this, gold, they are more than gold, you know. So they have, but at first the people call them real Earth. Now we know they are not so real, okay. But we still call them, sometimes we still call them real Earth elements. But basically we call them landslides. Okay, the second series is about the actinides. So actinides is this series, okay, includes these 14 elements. And they are, basically their electrons are filled in 5f orbitals. And just only 1, 2, 3 are only you can find on Earth. Just only 5. And these, they are not stable. They can only synthesized in the lab. So they are also called synthetic elements. And of course, if you can also synthesize some elements like with the electrons are filled in 6f. Is it possible? Yeah. Who knows? Yeah.
So how do they make those elements?
What?
How do they make those elements?
How to make?
Yeah.
Don't ask me. I don't know. I don't know how to make. I think it must like nuclear reaction. Yeah, you radiated particles heat some, and then they can change it to this elements. So they can only synthesize, made in lab. In the area, they are not stable. You can't find it on the Earth. Okay. Okay. Now question: which of the following ions is diamagnetic? So what's in diamagnetic? Yeah. What is magnetic? What is diamagnetic?
That's the opposite of magnetic.
Of course, I know why. What is the reason? What's the reason to make them like?
Yeah, exactly. We just need. So smartest.
Oh, now you said your monitor is the smartest.
What is it? Sure. What is my? Let me think.
So what's the magnetic? Magnetic basically it should have single electrons, right? Yeah. So diamagnetic means no single, right? So which one doesn't have single?
It doesn't have what?
This one, right? Yes.
Yeah, I'm confused. What's
So this is the electric configuration of this element, right? So when they become cations, so 3, for example, this one lose 3 electrons, right? So all these 3 electrons will be lost, right? So it doesn't have single electrons, right? But for others, basically they lose 4s electrons firstly, right? So besides this one, any more? No? Yeah, only this one. because this one 3, and then if this one iron, so this 3, this one, this 2, and this one, it is still have like some singles, and yeah, if zinc 2 plus, yes, if zinc 2 plus, zinc plus is magnetic or not?
6 plus.
Zinc 2 plus.
It's not magnetic.
I don't know.
No, it's not.
Yeah, it's not.
Yeah,
Because
it's
if you
just
lose
the
this 2, right?
Yeah.
So it's also no
Yeah.
single electrons.
No single electron.
If zinc 3 plus,
Yeah, it's magnetic.
yes, but no single definitely is just only. Sometimes you single 1 plus. Okay.
Diamagnetic.
So here, yeah, is the so the answer is this one. This one is homework. No, this you have, so this is the end of this chapter. That's all for today.